Now, for rewriting this expression, the final energy EF can be written as EE plus E nu. That is, final energy is the sum of energy of electron plus energy of neutrino. And we are writing energy of neutrino as Q into C, where Q is momentum and C is the velocity of light. Normally, you can write the energy as momentum into velocity. And differentiating this EF at a constant EE, you will be getting as dEF by differentiation of EF with respect to EF will give you 1, and EE is a constant, so it is 0. C into dQ by dEF, or from that equation dQ by dEF you can write as 1 by C. And substituting the value of dQ by dEF in the previous expression as 1 by C, we can get the expression for d lambda like this. And in this, now what we are doing is, this is H cross and this is H. Now you can replace this H with H cross by dividing this with 2 pi whole raised to x whole raised to 6. Then again you have to, if you are dividing with that number, you have to multiply also. So you can have a simplification based on this, and you can now get the result as d lambda equals g square by 2 pi cubed c mfi square h cross raised to 7 p square q square dp. And of course, this expression can be simplified or can be checked yourself. You can get the answer. And this expression of the last one, this expression gives the Fermi distribution for the emitted beta particles. By combining all the factors into a constant C, that means those factors that do not involve the momentum, the number of electrons with the momentum between P and P plus dP is. This is our expression, and in this, all these terms are independent of momentum. So this will become C, and you are writing that d lambda as it is the number of electrons in the momentum range P and P plus dP. You can replace it as n of P dP, that is equal to C P square Q square dP. And now, if capital Q is the decay energy, then that energy is shared as the kinetic energy of electrons and neutrons. So this Q you can write as TE. TE is the kinetic energy of electron, and QC, momentum into velocity, that is the kinetic energy. Okay. So this is the energy of neutrino. From that, the expression for momentum of neutrino you can write Q as Q minus TE by C, where this TE is the kinetic energy of electrons, and in the relativistic calculations, you have to take that TE as root of P square C square plus ME square C raised to 4 minus ME C square. And the same equation actually you are using for neutrino, but there this rest mass is 0. So you are getting only as root of q square c square. Root of q square c square is qc, and that is this expression. And the expression for momentum distribution becomes n of p dp cp square. In place of q square, you have q minus te the whole square by c square dp. This equation gives the spectrum shape and it vanishes at p is equal to 0. That means if this p equal to 0, this equation is 0. That means number of electrons with the momentum p as 0 is 0. And also at te equal to capital Q, you can see that when Q is equal to T, this is 0. That means NPdP is 0 at P equal to 0 and TE equal to Q. The momentum distribution is shown in figure, and this has a shape similar to that obtained experimentally. So this is the momentum distribution. That means this is NP and this is P. You will be getting almost these 2 points we have already mentioned. At P is equal to 0 and at P is equal to, for that is a maximum momentum. Corresponding to that, you have T is equal to Q. Again, that value must be 0. So you will be getting a curve like this. And this is the curve that we have proposed by deriving an equation, and a similar curve, and almost a similar curve, you can get by experiments, and this is an experimental curve. So this shows that the things that we have done is a valid one. And this is the momentum distribution curve. But normally we are interested in energy. In the starting section itself, we have drawn the energy distribution of beta t. So now we are trying to convert this expression for momentum in terms of kinetic energy, and that we can do in the next session.